Hello and welcome to another episode from Spiral Physics Education. So in this episode we're going to be looking at charge, we look at the definition of current, the equation that comes from that definition of current, conventional currents, ammeters and their role with current, and the current rules for both series and parallel circuits. So loads to get through. So let's get on with it. Unit of charge. So charge is measured in coulombs. And what we need to remember is that electrons have charge. And they've got a charge of minus 1.6 times 10 to the minus 19 of a coulomb. They have a very, very small amount of charge. And when we talk about charge building up, what we're talking about is electrons building up. So the more charge there is, the more electrons that are being involved. So you can imagine that if there was one electron, it's got a charge of 1.6 times 10 to the minus 19 coulombs, just ignoring that minus sign for the moment. If we have two electrons, we've got twice that. 3 electrons 3 times, 4 electrons, and that charge just builds up and builds up and builds up while we've got more electrons. So let's think about how many electrons will be required for a charge of 1 coulomb to build up. So what I'd like to do is just stop the video and see if you can calculate how many electrons there would be if we had a total charge of 1 coulomb. So if we think about it, the total charge is going to be a certain number of electrons, n, times by 1.6 times 10 to the minus 19 coulombs, the charge of that electron. And if we rearrange that, what we end up finding is that 6.25 times 10 to the 18 electrons is required to have a total charge of 1 coulomb. And what I'd like to do is visualize that like that, a cloud. So there are 6.25 times 10 to the 18 electrons in that 1 coulomb. And just visualize that as your visual aid to what 1 coulomb is. And we will discuss and mention 1 coulomb quite a lot, and it's important that you have a visual aid at your disposal to help you visualize what's happening to that 1 coulomb or with that 1 coulomb. Okay, so current. Well, current, we're going to have the symbol I for current. And that's because historically that's thought to be intensity of electricity back in the old days. So it's got the symbol I, and its definition is the rate of flow of charge. And there's a useful equation that comes from that definition, and that is charge over time. And remember that rate of, all that means is you're dividing by time. So anytime that you see rate of, it means that the denominator of the equation is time. Current must be in amps, it's really important. Charge must be in coulombs, and time must be in seconds, and those units are vital to getting full marks in any questions using this equation. So if we look at some more in this equation, charge has the symbol Q, and it has the symbol Q because it's thought of as quantity of charge. So it's important that you remember what each of the symbols means in this equation. So we've got this equation, current is charge over time, or I equals Q over T. So if we had 1 coulomb flowing through a circuit, for a point in a circuit, and it takes 1 second, we can visualize it as a cloud moving like this. And if we had 2 coulombs, it would look like that. And 2 coulombs in 1 second would be 2 amps. And 1 coulomb in 1 second would be 1 amp. So you've got a visual aid there of just more charge moving around for a period of time compared to 1 amp where we'd have 1 coulomb per second. Okay, so you get that visual aid. So let's have a look at you using the equation. So this is a typical exam question. Examiners are horrible because they do this to you. On the surface of things, you think, oh, I know that equation, Q equals IT, I can use it quite easily. But the problem is they've got the units, they've snuck in horrible units, and they've put in millicoulombs here. So the first thing that you need to do is convert those millicoulombs into coulombs, and you do that by dividing by 1,000. The easiest thing to do is to use standard form. So 5 millicoulombs is 5 times 10 to the minus 3 coulombs. Once you've done that, you can just use the equation I equals Q over T, substitute in your values, and you get an answer of 0.017. And if you're comfortable with standard form, you can do that or if you're comfortable with converting it and using milliamps, you can do that as well. But any of these answers fine, but do get comfortable with standard form. So look at another example here. So this time we've got 2.5 amps flowing for 2 minutes. We're going to work out how much charge flows from the power supply. Look at the units again. They've been sneaky, they've put minutes, so it's not just a case of multiplying 2.5 by 2 here. First thing we need to do, convert the minutes into seconds. And then use the equation. But we need to rearrange it, so get good at rearranging equations. So we're asked to calculate the charge, so it's Q equals IT. Now we can substitute in 2.5 times 120, so we get 300 coulombs of charge flowing through the power supply. Last example, an ammeter measures 0.75 amps, charge of 55 millicoulombs flowing through it. But we've got to give our answer to two significant figures, so there's another layer of complexity here. First thing though, done that thing again, millicoulombs, convert millicoulombs into coulombs, divide by 1,000. So 55 millicoulombs is 55 times 10 to the minus 3 coulombs using standard form. That's the equation that we're going to use. We need to rearrange it for time equals. So T equals Q over I. And now we can substitute in our answer. And what we get there is 0.073 seconds, or 73 milliseconds. So those are our a couple of examples of using that equation. Next thing to look into is conventional currents, and the first thing to realise is that power supplies have a positive and negative terminal. So in this simple circuit we've got a cell and a resistor attached to each other by some leads. The long terminal is the positive terminal and the short terminal is negative, but usually we just signify which one's positive and negative, so that's the positive terminal there. And when we're looking at conventional current flows from the positive to the negative terminal. And that's due to Ben Franklin in 1752 coming up with the idea that charge flowed in this circuit, but he didn't know whether the electrons involved in that, the charge was positive or negative, because about 150 years later J.J. Thomson discovered the electron, and that's when we knew that electrons had negative charge. So for about 150 years there were lots of books written and science evolved using electricity, thinking that current flowed from the positive terminal to the negative terminal. Instead of what's happening to the electrons is this. So at this point you're sort of thinking, well, do we go back and rewrite all the books and tell everyone who's dealing with electricity that everything's flowing in the other direction? Because the consequences of that are very, very dire, especially if you get it wrong. If you can imagine the current flowing into, let's say, a hairdryer the wrong way, it would suck instead of blow. You don't really want that happening. So what they decided to do was stick with the convention. So the convention is that current flows from the positive terminal to the negative terminal, and we've stuck with it. Ammeters, though, so here we've got our coulomb, and our coulomb is doing this for our conventional current. And we stick ammeters in series with the devices that we want to investigate. So an ammeter here would not only tell us how much current was being supplied by the power supply, it would also tell us how much current was flowing through the resistor. So in this case, we can place it in series. So let's think about a situation where we've got we've got in 2 seconds, let's say we've got 1 coulomb flowing through this ammeter. And we can then measure how much current is flowing. So we've got current is charge over time, and we've got 1 coulomb in 2 seconds. And that means we've got a current flowing through that resistor of 0.5 amps. So that ammeter then will read 0.5 amps. But we could place the ammeter after the resistor, and if you look at the animation's okay actually. The rate of flow of charge is the same everywhere in the series circuit, so it's 0.5 amps after the resistor. So we could put the ammeter in either position, but in fact we could put it anywhere else in the circuit. We could put it here, We could put one here, there. We can put it anywhere. But the thing is, we only need one. So as long as we put it in that ammeter in the right place, we just need one of them. And it's absolutely fine there. So current is the same everywhere in a series circuit. So as long as you put the ammeter in series, it will tell you not only the current being delivered by the power supply, but going, in this case, to this resistor. Parallel circuits are another kettle of fish though. So here we've got two identical resistors in parallel to each other. So they're the same value resistor as that other example. So that top resistor is going to have or draw a current of 0.5 amps, and I've animated it to show you that coulomb that's being supplied by the power supply flowing through that resistor. Now, because the bottom resistor is identical, the coulomb that flows through it is going to flow through it in exactly the same way in which the coulomb flows through the top one. It's got the same resistance. And that means the same current will flow through it. So there's going to be half an amp flowing through the top resistor and half an amp flowing through the bottom resistor. So that means the power supply, if we put an ammeter there, is supplying 1 amp in total. Let's think about adding a third identical resistor though. So if we add a third identical resistor in parallel, we've still got those two that are doing what they were doing before. But now we need to think of this third coulomb. So we've got a yellow coulomb, and that yellow coulomb is going to flow through that bottom resistor. And because that bottom resistor is identical, that means that it's got a current of 0.5 amps flowing through it as well. So let's think about the current that's being delivered by the power supply. It's 0.5 and 0.5 and 0.5. It's 1.5 amps in total that power supply is pushing around that circuit. What about an ammeter here though? Well, if we've got 1.5 amps flowing into this junction and half an amp flows out, that means there's 1 amp left over. And that means we've got 1 amp flowing into this junction, but if half an amp flows out to the second resistor, then only half an amp remains. Let's have a look at the other side of the circuit. So the other side of the circuit, if we put an ammeter here, we've got to think that we've got half an amp flowing in, half an amp flowing up. That means there's a total of 1 amp going into that junction. And if we think about half an amp flowing along that top resistor, we've got that half an amp and 1 amp. That means that we've got then 1.5 amps flowing back to the power supply. And there's a bit of symmetry going on there. And what that means is that the current is conserved at a junction. Whatever flows into the junction must flow out of the junction. So, to summarise series rules, current in series circuits is the same everywhere. Doesn't matter where you put the ammeter, as long as it's in series, it will tell you the current flowing through that circuit. Parallel, it's a little bit more tricky, so I'm going to spend a bit of time making sure you understand this summary. So in this case, I've identified the junctions A, B, C and D. And let's say we've got different resistors this time, so the current flowing into that top resistor is 1 amp, and they're all identical. We've got 1 amp flowing into that second, and we've got 1 amp flowing into that third one. And that means we've got 1 amp flowing across that top part of the circuit, 1 amp through that middle part of the circuit, and 1 amp through that bottom part of the circuit. So let's have a look at these two current values here flowing into junction D. So if we've got 2 amps flowing into junction D, that means we must have 2 amps flowing out of junction D. Current is conserved. Let's have a look at these two flowing into junction B. We've got 1 amp and 2 amps flowing into junction B. That means we must have 3 amps flowing out in total. Let's have a look at the other side of the circuit. Other side of the circuit, let's have a look at these two currents flowing out of junction C. We've got 1 amp and another 1 amp. So 2 amps must be flowing in. And if we look at these two current values flowing out at junction A, we've got 1 amp and we've got 2 amps, a total of 3 amps. That means a total of 3 amps must be flowing into junction A. So at a junction, whatever flows into the junction must flow out of the junction. Current is conserved. So, hope you found that introduction to current and circuits useful. Don't forget to subscribe to the channel to help get your understanding of physics up to speed and boost those grades in time for your exams. I'll see you next time on Spiral Physics Education. Goodbye.